Tracking water along the Szigetköz Danube. Hungary is just a little patch on the map of the world. Within this little patch, the Szigetköz is an even much smaller area along the river Danube. Nevertheless, this very little area is being widely discussed at present, even at international scale, in relation to the Bős- or Bős-nagymaros hydropower scheme and to the diversion of Danube from its channel. The Danube enters the Carpathian Basin at the Dévén Gate, near to Pozsony or Bratislava. The slope and sediment-carrying capacity of the river is decreased here to such an extent that the rougher sediment particles are being deposited in this river reach onto the channel bed. Thus, the river flows on the top of her own alluvial cone, forking into several branches. The two major side arms of the river surround areas which are called the Csallóköz and Szigetköz, respectively. Overlying the several thousand meters thick marine deposits of the Pannonian Basin, the quaternary gravel deposits of the river Danube extend down to several hundred meters below the ground surface of the Szigetköz. This gravel layer contains groundwater of several cubic kilometers magnitude and of drinking water quality. The Danube feeds daily into this aquifer approximately 1 million cubic meters of water, thus supplementing and refreshing this water resource. This area in itself is of unique value due to the rich geological formations, to the unrivaled diverse ecosystem, and also to the peerless landscape. While looking at the aerial and other photographs and films of this area, one should never forget that one of the most significant freshwater volumes of Europe is found under this area, and that this water resource is being fed from the river Danube. The mean rate of flow of Danube is about 2000 cubic meter per second along this reach, with the low flow being the half of this value and the flood flow being more than 4 times as much. The water level fluctuates in function of the river discharge within a 6 to 7 meter wide range. The fluctuation of the groundwater level follows that of the river stage, even at several kilometer distance from the river within 1 to 2 meter range. High waters occur in the spring, while low flows characterize the autumn. The surface slope of the river is 30 to 14 cm per kilometers along the Szigetköz reach, and the flow velocities are rather high. The characteristic flow velocity of 2 to 3 meters per second hardly drops below 1 to 2 meters per second, even at low flows. Due to this high velocity, the fine suspended sediment is being deposited over the floodplain and in the side arms only. Thus, the channel bed of the main river branch is formed by clean-washed gravel. The upper ends of the side river arms had been closed off during the river regulation with rock-filled dams which allow overflow at high water levels only. The reason of this regulation was to prevent the river flow from spreading into the channels at lower than mean water stages, thus securing navigation water depths. Due to this situation, there was no water feeding to the channels through the overflow dams for about 3 months in a year, not even before the diversion of the river. There were also entire years without overflow, that is, when the water stage of the river Danube did not exceed the crest level of the closure dikes. Under these conditions, considerable seepage flow of crystalline cleanness is feeding the side river arms through the dikes, and the side arms with open downstream end receive also inflow through these openings. In 1977, Czechoslovakia and Hungary signed an agreement on the construction of the Bős or Bős-nagymaros hydropower scheme. According to this plan, the river would have been impounded by the Dunakility Dam in order to divert water through a power canal to the turbines of the Bős or Gabčíkovo hydropower station, and then by the tailwater canal back to the Danube. This would have left 50 to 200 cubic meters per second flow only in the main channel of the river. In order to maintain appropriately high groundwater level, that is to avoid the subsidence of the groundwater table, bottom dikes were to be built in the main channel, associated with a flow supplementing system which was to divert seepage flow to the channels of the side river arms of the Szigetköz area. The Hungarian partner refrained from this agreement in 1989, claiming that very high environmental risks are associated with this scheme. The Czechoslovak partner did not accept this claim and considered the agreement still valid. In October 1992, Czechoslovakia built a river dam at Dunacsúny upstream of the common border section of the river Danube and diverted the river flow to the hydropower station. Since that time, 250 to 350 cubic meters per second flow has been released into the main channel of the Danube, with the exception of flood flow periods, which is only 10 to 20% of the original discharge. Due to this diversion, the water level of the river sunk by 2 to 3 meters, and water has disappeared from a substantial part of the side river arms. This was associated with the sinking of the groundwater table by about 1 meter in the vicinity of the channels. In the dried out parts of the main channel, vegetation has rapidly been gaining space over the gravel bed, retaining much silt and mud after the floods. Hungary had requested the releasing of the larger part of the original river flow into the main channel, but this has been refused by the Czechoslovak partner. In order to mitigate damages, Hungarians attempted to provide supplementary flows into the floodplain. Similar strategy had been applied in the Slovak side earlier, but there was abundant water available for this purpose in the river impoundment. On the Hungarian side, the only water available for such purposes, with appropriate hydraulic head, is the flow of 20 to 30 cubic meters per second of the main side arm, the Mosoni Danube. Another solution can be the impounding of the remaining low flows of the main Danube channel to a stage which allows the feeding of water into the side river arms. This latter solution, however, endangers the conditions of the main channel because the thus reduced flow velocities would be associated with high silt deposition. Consequently, the former strategy, the diversion of flow from the Mosoni Danube, has been applied with an experimental character. The experiment started in early August 1993. In contrast to the expectations, the flow of 12 cubic meters per second, which discharged into the floodplain, did not filtrate into the soil right in the vicinity of the diversion, but was conveyed through the interconnected side arms of the floodplain. This indicates that the channel beds of the side arms have been clogged with fine sediment particles to a higher extent than that of the main river. Several tens of cubic meters of flow would be sufficient for the maintenance of the water levels of the side arms at the desirable stage, and with the increasing clogging of the gravel bed, this rate could even be lowered if there were no lower limit set by ecologically desirable minimum flow velocity. Although the supplementary flows can be provided for the side arm system, even if not with the original conditions, this will solve the problems of the sinking groundwater table by no means. This solution cannot substitute the inflow to the groundwater which had earlier been provided by the high rates of flow which moved in the gravel bed under the main river channel. The abandoned channel of the river Danube have been repeatedly surveyed by experts. Undesirable changes have been identified in those parts of the channel rarely covered by water. If water levels were increased with the help of bottom dikes, then the gravel surfaces of the narrowed down low flow channel would become upsilted as well. What might surveys show in a few years? Prediction is very difficult. For on one hand, we have reached the limits of the ability of measuring and predicting natural processes, and on the other hand, the prediction of the changes of the society's judgment of values would also be necessary. The question is it more important to generate clean energy and to navigate in an economical way now? Or is it more important to preserve the semi-natural hydrological regime, the river flow which can secure the availability of clean, bank-filtered water resources and the ecological diversity of the unique biota of this region for generations to come? These questions should have been answered much earlier.